This video is the first in a series that will go through different types of proof. The first type, and the one you may be most familiar with, is direct proof. You may have already covered this topic but were not aware of it. You can see from the definition that most questions that start with a show that something is equal to something else would be a direct proof question. This video will focus on 2 points. Firstly, how to correctly lay out a direct proof, and secondly, how to decide the logical steps to make. This is why I've used this definition, because I want to emphasize that steps made to prove something should be logical and not random. It is not by chance that you should end up with the desired expression, but through a series of logical steps. We will do this by looking at examples and trying to generalize the approach. To start with, let's talk about the structure. In a proof, we are starting off with a single expression, not an equation, and working towards a goal. In this first example, I want to work from one side of this equivalence to the other. I do not want to manipulate both sides at the same time. This would mean I've already assumed the two things are equal before I start. In the types of proofs I will go through in these episodes, structure is very important. You can always fall back on structure if you are finding the question difficult. For the first question, I will start with the left-hand side. Now I need to make a logical next step. What would you do? If you have made a decision to expand without thinking why, then you are not making a logical next step. Our goal is the right-hand side, which has a factor of x minus 1. We are starting with the left-hand side, which is two separate expressions, both with x minus 1 as a factor, and we want to head towards a single expression. Therefore, it makes logical sense to factorize the x minus 1 out. I can then expand inside the second bracket and factorize again to get the right-hand side. For the next example, I'm going to start with the right-hand side, because I think it is easier to combine two terms into one fraction, rather than to split one fraction up. This is because I have taught students before adding algebraic fractions. If you are more comfortable splitting up a fraction, then it can be done by factorizing the numerator using the denominator as the factor. Then we add on 4 because we want to make sure this step is equal to the previous one, as there is an equal sign. You can always check your working by thinking about whether the expression you have written down is equal to the previous one. Now we can split up the fraction into two parts. It was logical to take that factor of 3 out so I could work the denominator into the fraction. This type of forcing in a factor is similar to completing the square, where you correct yourself at the end by subtracting the constant. And now I get the right-hand side. Whichever way you choose, remember the structure of moving from one expression to the other through logical manipulations. The next two examples are those where we must form the algebraic expressions ourselves, and then we can logically manipulate. Here, in the first question, our goal is to end up with an even number. I'm going to use 2 times n minus 1 and 2 times n plus 1, where n is an integer, and these will represent my two consecutive odd integers. I'm using minus 1 and plus 1, as I know when I expand, things will cancel out. It makes logical sense to expand, as the only other option would be to factorize, but there are no common factors here, so I can expand and then simplify. I now get down to an expression I can factorize by taking 2 out. This makes logical sense, as 2 multiplied by any number will be an even number. And this is my goal. The next part of my logical argument is to make this statement. As I mentioned at the beginning, logical arguments can involve statements as well as algebra. The next question is slightly different, as I am looking at the difference of any two odd numbers. So I'm going to use 2n plus 1 and 2m plus 1, where n and m are integers. Again, it makes sense to expand, as there is nothing else I can do, and then I can simplify. I can now look at factorising, and we can clearly see that 4 is a common factor of each term. However, this factorisation doesn't tell me that much, or I can't see clearly what it tells me at the moment. So I'm going to try and factorise in a different way. Factorising in this way leads me to wonder why each term is a factor of 8. They are already factors of 4, so if n times n plus 1 and m times m plus 1 are even, then I will have an extra factor of 2 to go with the 4, making each expression a multiple of 8. Well, I can now consider cases. If n is even, then I will have an even multiplied by an odd number, because n plus 1 will be odd. And even multiplied by an odd is even. The other case is if n is odd. In this one, n plus 1 will be even, and again I will have an even result. The same will be applied to m and m plus 1. I can then make this statement as the end of my proof. I could also consider cases in the previous factorisation of n squared plus n minus m squared minus m. Think about the different cases yourself of n and m, and explain why that expression would therefore be even. I've included this next example just to give another proof where writing consecutive numbers using a negative 1 and a plus 1 is helpful. This technique can also be used in sequences and series for consecutive terms in arithmetic and geometric sequences. Here I can see that n minus 1 and n plus 1 will multiply together to give n squared minus 1. I can then multiply by n and add the middle term, as stated in the question, to give n cubed, which is clearly a perfect cube. This can also be solved by using n, n plus 1, and n plus 2 as my three terms, but it doesn't simplify as nicely. The logical steps here do seem to be reduced to what is my only option. So let's get back to some examples with logical steps. The next question asks us to add two rational numbers to prove that the result is rational. I can express a rational number as one integer over another. So a, b, c and d are all integers. I want to combine these two rational numbers into one rational number. So the logical step to make is to add these two fractions together by making the denominators the same. This does indeed lead to a rational number, as both the numerator and the denominator will be integers. The next question will also look at the manipulation of fractions, but in a different way. For this proof, what can we do to manipulate this fraction? To manipulate a fraction, I could split the fraction up, as shown in the previous question, or I could multiply the top and bottom by an amount, or divide the top and bottom by amount, to keep it an equivalent fraction. It can be logical to rationalise the denominator, as our goal is an expression that does not have a third as a denominator. We can see this has a desired result. Keep this in mind that if you have a fraction in a proof, then a manipulation is to multiply or divide the numerator by the same amount, as well as thinking about maybe splitting up that fraction. I will finish with a trigonometry show that question, to show that another form of manipulation can involve identities. I will start with the left-hand side of this equivalence, as it is easier to take something complicated and simplify it, rather than taking something simple, like tan x, and making it more complicated. My goal is to head to tan x, so it would make sense to manipulate the trigonometric functions that have 2x as their angles, rather than just x. I can therefore use double angle identities, so all trigonometric functions in this fraction have x as the angle. This is a logical step. Sine 2x is a simple identity, as there is only one option. Cos 2x, however, is more complicated, as there are 3 forms to choose from. So I need to make a decision, and there needs to be a reason for that decision. Which option would you choose? I will use 2 cosine squared x minus 1, as then the plus 1 and minus 1 will cancel out, making the denominator simpler. What next? What can I do to the denominator and numerator? The answer is I can factorize. Did you spot the factorization? You should always look out for factorization when you have 2 or more terms. Ask yourself if you can factorize, whether it's a proof question or whether it's an equation. This gives me a common factor in the numerator and denominator, which will cancel out, leaving me with tangent x. Take a moment to reflect or take notes on how I've manipulated my expressions, what logical manipulations I have made. All these techniques should be in your head when approaching a direct proof. We will see some of these methods in the next video, which will look at proof by induction. We will need to use the same structure and strategies I have used here in order to reach the goal of the final step in the proof by induction. I hope this video has been helpful.